Okay, this one's a little PowerPoint about expansion devices. Just kind of tells which ones are available, pretty much how they work. Okay, two types are most common. Thermostatic expansion valve, which has been around for many, many years. The first ones I heard of were put in the 20s. But been used for a very long time. It can be called a TXV, TEV. My dad used to call them a thermal valve. Here's how this works. It works on evaporator superheat. It doesn't work on coil temperature, box temperature, anything like that. It works on evaporator superheat. That's all it cares about. Okay, it has a sensing bulb. And that sensing bulb is mounted at the outlet of the evaporator. And it's going to sense the temperature of the pipe at the end of the evaporator. So it can tell how warm the pipe is, which tells you how much superheat you have. Let's say you had a evaporating temperature of 40 degrees and the temperature at the end of the evaporator was 50 degrees, you'd have 10 degrees superheat. So that's what it's doing. Okay, it must be mounted on the line, suction lines that comes out of the evaporator. And it should be clean and tight, and we generally insulate it. Not everybody insulates them. Trane, I noticed, never does insulate theirs, but mostly they are insulated, especially if it's a medium temp box or a low temp box other than an air conditioner. Okay, here we're looking at a suction line right here and a bulb, and it's got a strap that straps around the suction line and holds it tight. You may have two of them. Okay, 7/8 or over suction line, you mount it on the lower quadrant. Now, if it's under 7/8 inch suction line, you put it on top of the line. You never put it on the bottom because there's oil and there's a little bit of liquid refrigerant in there. So that's going to give you a poor reading. Or, as usual and everything else, manufacturer's instructions. As the suction line temperature increases, the bulb temperature is going to increase. As the bulb temperature increases, the saturated temperature pressure increases. The increased pressure overcomes the spring and the suction pressure. You'll get a view of this one in a minute, and opens the valve. Now remember, this is a modulating valve. It opens part way. It doesn't open all the way. Well, it does at first. It opens all the way when it first starts, but then it modulates. Okay, now here's a picture of the expansion valve. Now, my wonderful animation here, I know you'll be just terribly thrilled with it, but let's look at it. Okay, I have a saturated mix in the bulb of, and it's usually the refrigerant that's in the equipment. I mean, there are some other types of charges, cross charges and so on, but this will have liquid in it and it'll have gas, and it's sensing on that suction line, and with this cap tube comes up here and puts pressure here on this diaphragm right here. And these two shafts move down like this, and they open the valve if the pressure is high enough. Now there's a spring down here and it's pushing to close the valve, and the suction pressure that's inside here is trying to open the valve. Okay. Now you can see the little bubble things go up there, you know, it's getting hotter. Okay, this moves down So the refrigerant comes through the open valve, and it's going to, the more refrigerant that goes through, the lower the superheat's going to be, and that's going to decrease this pressure up here, and the valve will begin to close. Okay, it's pretty much what I was saying there. Flow increases, suction temperature reduces, bulb temperature reduces, spring suction pressure overcomes bulb pressure, and valve closes. Modulates close, we'll call it that. The pressure changes result in that modulating effect, and when it reaches equilibrium, that means the suction temperature is correct. That means the superheat's correct. It holds at that position. Now, if I add more load, let's say I had a reach-in box and it had reached temperature and it was running, okay, it's going to be fairly, the valve won't be closed, but it'll be close to it. If I was to put warm product inside that box, that warm air is going to come up through the evaporator, and it is going to increase the evaporator pressure and increase the superheat. And as that superheat increases, it's going to open the valve more. And that compensates for the increased load. Again, the only thing it cares about is superheat. Suction pressure, head pressure do not generally affect the operation. I will say if your head pressure gets extremely high compared to your suction pressure, that will affect the operation if it's out of spec high. Okay, advantages. Very adaptable to load conditions. These are the type of valve that if I was to take a walk-in box that was empty and it was to temperature and it's running, and let's say I put 50 halves of beef in it. Okay, this is going to adapt to that load. As soon as they come out, or they put the product in there, then this thing is going to open up and adapt to that load. Pretty much the highest efficiency you can get is done with an expansion valve, a TXV. I won't say all high efficiency units use them. Some of them use fixed orifice devices, but it's the easiest way to make high efficiency. To a certain extent, it will compensate for things like plug filters or plug coils, low ambient operation. These units will actually work at lower ambience, outdoor ambience, than fixed orifice devices without freezing the coil. Doesn't mean they'll do everything. If it's too far, they'll still freeze up. Will generally operate under poorer conditions. One of the things these valves are really good at, they are the engineer of the system. I do not have to make a highly engineered system to get it to work with a TXV. It will work with things that aren't balanced too well and so on. It will fix to a certain extent any out of spec conditions. Very, very good control of superheat. One of the things about this, because it controls superheat so well, it pretty much eliminates, not in all cases, but in a lot of cases, it eliminates any compressor slugging. Once this thing is running, it's unusual for them to slug a compressor. Okay, very good control of superheat. Charge is not critical with these things. Like I said, it is the engineer. You don't really have to be the engineer in this thing. Okay, disadvantages. There are bleed and non-bleed TXVs. A bleed TXV means that it has a little bypass, and when the unit shuts down, it will bleed the high side to the low side and equalize the pressures. Most of them are not equipped that way. And if they aren't equipped that way, the low side pressure will come up to what the low side temperature pressure, saturation pressure is, and the high side will go to whatever temperature pressure it's at, and they're probably not the same, and the compressor will have to start against a head. That means a head pressure that's higher than the suction pressure. So they usually have to have a hard start in the compressors. It's a fairly expensive valve compared to fixed orifice device, and there are potentially more moving parts to fail. I don't want to say these valves are not dependable, because they are. They've been around forever. Their design is pretty well set, and I have seen them run up to 50 years. So, but potentially there are no more parts to fail. Okay, let's talk about fixed orifice device. These are usually two different types of devices. One can be a capillary tube. A capillary tube is just a very small diameter tube, and I'll have a picture on one of these things here in a little bit, that restricts flow just because of its size. Now, maybe more than one capillary tube. Or we have a check valve that will allow refrigerants to pass through with no pressure reduction one way, but if the refrigerant's going back the other way, then it will restrict the flow because there's a hole in it. It's a precisely drilled hole that restricts flow. Okay, here's my capillary tube. It's usually kind of coiled up like that, and the friction with the walls of the tube will reduce the flow. Okay, this is actually a unit that uses capillary tubes, and it's got 4 of them, because there's actually 4 different coils inside this one single coil. And you'll see this one here is going down and around and over to there, and you know they're feeding each individual coil. Unless the unit's very small, it'll have multiple capillary tubes. Okay, a check valve, and it'll bypass and flow full flow in one direction and restrict in the opposite, as I said earlier. Okay, here's another one of my wonderful animations. Let's take a look at this device here. This hole in the center is going to restrict flow. Now, if I look at the end of this, it will have some sort of seats out there that block how far it'll move. Well, let's take a look at this thing in operation. Okay, we're in a restricted position right now. Refrigerant can't go through here because it's blocked off by this part here. But it can go through here, so it restricts. Now, if I move the refrigerant the opposite way, then it can both go through here and it can go around the check valve. And so it'll be full flow. Okay, they're oftentimes used in heat pump applications. They are using air conditioners anymore too, because if you change the size of the orifice in it, it adapts it to different pieces of equipment. But heat pump applications were actually the first ones that they used this on. And it was to provide the same thing as a capillary tube, but if you reverse the flow, then it would bypass and not have any restriction. The fixed orifice device controls flow by the pressure difference between high side and low side. It's not just head pressure, it's not just suction pressure. It's the difference between the two. Okay, as the load increases, the suction pressure increases, and the volume of vaporized refrigerant increases. So you get an increased volume of gas that goes through the evaporator, is through the compressor, and reaches a condenser and fills the condenser more full, and that gets more load, more to BTUs going to the condenser, and the head pressure increases, increasing the flow through the fixed orifice. So if I took a unit, now let's say I had an 85 degree outdoor ambient and a 75 degree indoor ambient, I would get a certain amount of flow through this thing because of how much refrigerant is actually passing through that, evaporating in the evaporator and condensing in the condenser. But let's say I increase my my indoor ambient to 80 degrees. If I did that, the suction pressure would increase, but it wouldn't increase a lot. It may increase 2 or 3 pounds or maybe 4 pounds. However, because I have a warmer return air coming in at 80 degrees rather than 75, it's going to absorb more BTUs from the air that's passing across. Those more BTUs go through the compressor and into the condenser, and the condenser has to work harder. It has to pull more heat out, so the head pressure increases. And that increases the flow through the fixed orifice. I'm going to do a little bit of a comparison here. This is taking, let's say I had a head pressure of 200 pounds and suction pressure of 68. Okay, the pressure difference is 132 pounds. The head pressure, let's increase the head pressure to 275 pounds and the suction pressure to 72. Now we've got 203 degrees or 203 pounds of pressure difference. And so there's going to be more flow through that thing. So more BTUs absorbed and then more BTUs thrown off by the condenser. That's how it adapts to load. Charge is very critical in these things. Okay. When I say it's adaptable to changing loads, by what I was just saying, by the increase in head pressure compared to suction pressure, it will adapt to changing loads. But there's limitations on this. Not quite as good as a TXV. Okay, advantages. A fixed orifice of the cap tube is cheap, reliable to the extent that you don't have contaminants in the system, chunks of winding or sand or something, because they'll plug up pretty easy because they're pretty small. It does have some adaptation to load conditions, and it does not require a hard start device on the compressor because the hole's always there, and so it's going to equalize pressures in just a couple of minutes. Disadvantages to this system. Charge is critical. If, let's say, my charge was a little bit too low. If it's too low, then the suction pressure is going to be low and the head pressure is going to be low. And so if I reached a high load condition, it would simply just run out of refrigerant and the pressures would be too low to adapt to the load. So these things are really picky about their charge. You got to be right on the money. Also, I would not charge one of these things unless I knew that I had a clear coil, a clean evaporator, coil, blower, all that stuff has to be working properly. Airflow has to be up to par. You know, we love 400 cubic foot per pound. And if none of those things are there, you're not going to get the charge right, and it's not going to operate right. It usually, you know, you could be a ways off and it'll work, but it won't be as efficient, and you may end up with a overheated compressor, reducing compressor life. So here again, load adaptation is less than ideal, and highest efficiencies are, well, I'll say generally not possible, and of course it's easy to plug. So these are the two most common. There are other types of expansion devices. I may get into those later. Most of them are not real common. These are the two that you see in most units.